Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 25, 2026, just 2 days ago. It introduces a new framework called PhysicEdit that improves physical realism in image editing by roughly 6%, effectively bridging the gap between simple instruction following and actual physical plausibility. The paper is titled From Statics to Dynamics, Physics-Aware Image Editing with Latent Transition Priors. And as we'll see later, the implications for generating physically accurate scenes are quite significant. To see why this matters, Figure 1 illustrates the core problem with current editing models. In the top row, the instruction is simply to insert a straw. Notice how standard models like GPT Image 1.5 or Nano Banana Pro just paste a straight straw in, completely ignoring optical refraction. But the model on the right, labeled Ours, correctly renders that bent appearance at the water surface. Then, looking at the bottom section, we see a heavy ball falling onto a cushion. Existing methods might make it hover or shatter the object unrealistically, shown in the red boxes. The proposed method, however, treats this as a physical state transition, ensuring the cushion deforms naturally as the ball lands, which you can see in the green trajectory. To teach the model these dynamics, the authors constructed a massive dataset called PhysicTran 38K. Figure 2 breaks down the 4-stage pipeline. It begins in Panel A by defining a taxonomy of 46 specific physical transitions across domains like mechanical, thermal, and optical. Next, Panel B shows how they turn these concepts into structured prompts, specifying a start state, a trigger, and a transition, to generate synthetic videos using a model called WAN. Crucially, Panel C illustrates a rigorous filtering step, where they discard clips with moving cameras or physical inconsistencies. Finally, Panel D depicts the reasoning generation, where detailed text descriptions are created to ground the visual changes in language. So, having constructed the dataset, Figure 3 presents the PhysicEdit framework itself, which employs a dual thinking mechanism. On the left in Panel A, the training process passes an input image and instruction through a frozen Quinn 2.5 VL. It generates physically grounded reasoning text, like describing the mild reaction, while simultaneously learning latent transition queries. These queries are supervised by video features from Dino V2 and A versus AE to capture dynamic changes. Then, Panel B shows inference, where these learned queries guide the diffusion backbone to generate the final result. With the architecture defined, Table 1 reveals the quantitative performance on PicoBench. The top section lists proprietary giants like GPT Image 1.5, while the bottom focuses on open-source models. Crucially, if you look at the final 2 rows, PhysicEdit achieves an overall score of roughly 65, beating its backbone, Quinn ImageEdit, by nearly 4 points. The gains are even starker in complex dynamics. For instance, light source effects, shown in the LSE column, surge from 61 to 76, confirming the model's superior grasp of physical changes. Moving to the component analysis, Table 3 details an ablation study to pinpoint where these improvements come from. We see that standard supervised fine-tuning, labeled plus SFT, offers only a marginal gain over the Quinn ImageEdit baseline. However, adding the physical reasoning stream significantly boosts the mechanics score to 57.4, showing that textual logic helps with rigid body dynamics. In contrast, the visual thinking module excels at optics, raising that metric to over 68. Ultimately, the full PhysicEdit model at the bottom combines these strengths to achieve the highest overall performance. Table 2 extends the evaluation to the Core IS benchmark, which tests for broader knowledge and reasoning capabilities beyond just visual editing. In the top section, while GPT-4o remains dominant among proprietary models, PhysicEdit actually surpasses competitors like Gemini 2.0 and Dubao, with an overall score of 72.16. If we look at the bottom rows for open-source models, the gains over the Qwen ImageEdit backbone are clear. Specifically under conceptual knowledge, the natural science score leaps by nearly 12 points to 71.57, and temporal perception also improves, confirming that the model has internalized the physics of change rather than just surface patterns. So, while the tables showed the statistics, Figure 4 provides the visual proof by comparing qualitative results on the PicoBench dataset. In the top left, for the command turn off the lamp, notice how PhysicEdit correctly models the global dimming and shadow propagation, whereas the baselines often fail to render consistent lighting. Similarly, in the bottom right panel for freeze the soda can, the model accurately generates frost textures on the surface, confirming it understands the physical nuances of state changes. Wrapping up, the big takeaway is that treating image editing as a dynamic physical transition solves major realism issues. By learning from video data, the model captures the physics of change, ensuring light bends and materials deform correctly. This points toward a future where generative models respect physical laws as much as they do text prompts. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.